My name is Wang. I'm a researcher at New York University. I'm excited to present our work, VRGaitAnalytics, visualizing dual task calls for VRGait assessment. It is a walking balance assessment system that can help experimenters investigate individuals' gait performance during walking and obstacle coursing, and provide spatial data visualization to better understand and interpret the experimental data. Human balance is the ability to keep the body stable and prevent falling when standing or moving. It is essential for our health and quality of life due to its necessity in sports, exercise, and all kinds of daily life activities. According to the data from CDC in the US, falls are the top public health problem for older Americans. It could be more severe and costly than we thought. Over 25% Americans older than 65 experience at least one fall each year. Fall-related injuries bring one to the emergency room every 11 seconds and cause one death every 19 minutes. The direct cost of the medical attention for fall injuries reached $50 billion in 2015 and expected to reach $68 billion by 2020. Falls typically happen when changing environmental conditions, tripping over an obstacle, and multitasking. Changing environmental conditions brings multisensory cues and causes changes in multisensory input, including visual, touch, vestibular, and auditory input. Tripping over an obstacle and multitasking are another two common causes of falls, and particularly challenging for aging adults. They would be vulnerable to falls when stepping onto an obstacle such as a curb if they did not notice or could not clear it safely. They may also have difficulty walking safely when engaging in a secondary task, such as memorizing words or looking at phones. Our goals include understanding the relationship between balance and the stimuli of visual, auditory, and cognitive load. With all the causes of falls taken into account, we designed and implemented a balance diagnostic tool to assess balance with quantitative balance parameters and qualitative observations, examine the response to multisensory stimuli, investigate balance strategies such as obstacle coursing and avoiding a collision, and also making it accessible to clinics or even home use. Our day-to-day life requires performing concurrent cognitive tasks while walking, such as walking and texting, walking and navigating on busy streets, are all examples of dual tasking that combine walking with cognitive abilities. Performing two tasks concurrently might require more than the participant's total attention capacity, which impacts the performance of either task or both. This is called the dual task interference cost. The system has a dual task paradigm where participants need to memorize numbers while walking with or without negotiating obstacles. The system uses HTC Vive Pro to present VR environments with spatial audio. The headset combines a wireless adapter to make the VR headset untethered. Vive trackers mounted on the top of the feet to get foot kinematics. The VR system cannot provide somatosensory inputs of the foot to simulate the impact when a participant hits the obstacle. So the feet are represented by graphic foot models in VR for the participant to visually detect their own feet and identify if their feet clears the obstacle. The system also provides auditory feedback to indicate the success or failure of the obstacle coursing. We measure foot dimensions and foot tracker placement to align the foot models to their feet. The system provides three major stimuli: visual, auditory, and cognitive. Each of them has low and high intensity. The stimuli are independent variables which can impact the balance. Experiments can control the stimuli and present participants the permutations of the stimuli. The motor tasks include normal walking and crossing virtual obstacle during walking. For the obstacle coursing, the system can generate anticipated obstacle generated with a specific height at the start of the scene, so the participant can have enough time to plan the obstacle negotiation strategy. The system can also generate an unanticipated obstacle with the selected height, but at a random time. Participants will not be able to predict how far or when an obstacle will appear in front of them. Experimenters can observe how participants react to specific conditions, measure the balance, and investigate the underlying causes under different conditions. VRGaitAnalytics uses a spatial data visualization module to instantaneously provide VR playback and outcome measures to indicate gait performance. In clinics, experimenters and participants may have the demand to record and playback trials. So the system provides motion playback, allowing them to observe and interpret their balanced performance. The VR playback allows them to inspect the motion at any time of the trial. They can freely change their viewing position and angles. The VR users view the replay as an observer. The video shows how the system replays the trial. The avatar was driven by a recorded data, and the VR user can watch the playback as an observer. When watching their own performance, participants can learn how to plan a successful obstacle coursing and perform the task better. In addition, VR playback does not have confidentiality issues compared to video recording. The system can visualize the motion trajectory for each body segment. The trajectories are rendered behind the moving segments and could be useful for better visualization and motion interpretation. Overlapping the VR playback of the two trials and replaying them side by side simultaneously can make it easier to detect between trials difference, such as which trial has a lower foot clearance, longer step length, shorter step width, etc. So we implement the trial comparison module to load two trials playback data and replay them in the same time frame and the same place. Experimenters have full control over the display of the two trials. The two trials have different color coding for their motion trajectories and different transparency renderings for the segments. Experimenters can replay the trials from the beginning to the end simultaneously or jump to a specific frame. For each trial, there is a corresponding frame slider for users to pick any frame and align the starting point of the trial with the other trial. For example, users can use the frame slider to align two trials based on the moment of their second stride of the left foot and replace the two trials simultaneously from that moment. The measurement module calculates metrics in real time, such as walking velocity, step length, step width, the success rate of obstacle coursing. Experimenters and participants can select what metric to display and view the data plot of the metrics in VR or on screen. The outcome measure and its visualization can give them feedback and right away instead of waiting for an offline report. Our preliminary analysis for the step length and step width in obstacle coursing show that step length decreased, but the step width increased under high cognitive load compared to no cognitive load. The result supports previous study where healthy young adults demonstrated a shorter step length and a wider step width when walking and performing another cognitive task. This difference is caused by dual task cost. This project is the collaboration across NYU Krantz, Steinhardt, and Tandon. We are grateful for the funding from the NYU Aging Incubator. Thanks to all of them, and thank you for coming to our virtual talk.